Hello. I will present this work because the first author is unable to do so for personal reasons. It is a joint work between Dario Ferreira and myself with the title Hybrid EM and Bayesian-Stochastic Approximation Method for Variance Components in Incomplete Mixed Models. This is the outline of the presentation. And the traditional variance component estimation methods, as we know, are least squares, analysis of variance, maximum likelihood, and restricted maximum likelihood. But these methods, between many others, suffer from inefficiency in the presence of missing data, and they require computationally expensive likelihood maximization. So, to address these limitations, we propose a hybrid approach that integrates EM for missing data imputation and BSA for variance component estimation. Let's start by considering linear mixed models, as we have here in 1, with these conditions. The mean vector of the observations y is like we have here in equation 2, the variance covariance matrix of the observations y are in 3, where we consider matrices M I equal to xi transpose. One method, well known, is least squares method, and let's consider x and beta as we have here in equation 4, and let's consider the matrix A, whose row vectors A1, AG form an orthonormal basis for the orthogonal complement of omega. And let y dot L equal to this expression in 5. So y dot L will have 0 mean and variance given by 6, where BLI are given by L, A L transpose, M high, A high. In equation 7, we consider Z L equal to y dot L square. So the expectation of Z is equal to B sigma square, where Z, B, and sigma square are given by these expressions. The LSE for sigma squared is given by 9, where K has this expression, and plus denotes the Moore-Penrose inverse of the matrix. Another well-known method is ANOVA method, where the total sum of squares can be divided in the sum of squares due to the random effects plus SSE, the residual error, and we have this F statistic as we have here in equation 11. The variance components are given by these expressions, where n is the number of observations per level of the random factor in balanced designs. Another method is maximum likelihood method, and this method for a linear mixed model assumes the expression assumes that the observations follow this normal distribution, where V is the variance covariance matrix given by this expression. The log likelihood function is given by equation 14, and the ML estimators of the variance components are obtained by solving this equation in 15. Another well-known method is the restricted maximum likelihood method that is given by equation 16. The additional term in the end of the expression accounts for the uncertainty in estimating beta 0. And similar to ML, the REML estimators are obtaining by solving this equation. Now, let's move to our method. And we consider that given a data set with missing observations, let be O the observed data, C the missing data, and the complete data set we will represent by this. The EM algorithm alternates between two steps, the expectation step that we will call E step, and maximization step that we will call M step. The E step computes the expected complete data, log likelihood function as we state here in equation 18, and sigma squared t are the variance components estimated in the previous interaction. The missing values are estimated using the conditional expectation in 19, where v underscore 0, are the covariance is a covariance matrix of the observed data, and v underscore co is the covariance between observed and missing data. The variance of the missing data given the observed data is given by variance as we have in 20, where v underscore cc is the covariance matrix of the missing data. The M step updates the variance component sigma square by maximizing the expected log likelihood given by this equation 21. Although the EM algorithm provides a framework to handle missing data, it does not regularize variance component estimates. To improve estimation accuracy and stability, we incorporate Bayesian priors and use stochastic updates through the Bayesian-Stochastic Approximation method that we'll call BSA method. In the Bayesian framework, variance components sigma square 1, sigma square m are treated as random variables and assigned inverse gamma priors, as we have here in equation 22. The posterior distribution of each variance component is given by this expression, which combines the likelihood from the observed data and the prior distribution. And since the direct computation of the posterior expectation is intractable, we approximate it using a stochastic update like we have in equation 24, where gamma underscore t is equal to this, is the learning rate that decreases over iterations. The expectation is approximated via stochastic sampling, where k is a tuning parameter that controls the variance of the samples. So, the final variance component estimate is obtained by averaging over multiple iterations, like we have in equation 26. Now, let's move to a numerical application, where we will consider a case with two random effects vectors, A and B, each with 4 levels. The observation vectors can be rewritten as this. Beta 0 is fixed, beta 1 is independent of beta 2, and they followed a normal distribution. We analyzed 6 different cases by progressively removing observations to introduce missing data. In case 1, we assume complete observations that we have here in this table. Observations for the first case. We consider the observations vector y the matrix is x0, x1 transpose, x2 transpose, with x1 and x2 corresponding to factor A and B respectively. We generated y randomly, taking into account these values. For instance, when sigma square 1 is equal to 0.25 and sigma square 2 is equal to 2.25, we generate y where beta 1 follow this normal distribution and beta 2 follow this normal distribution. The variance components sigma square 1 and sigma square 2 were estimated using 5 methods. So, we have here the variance estimated for case 1. From case 2 to case 6, we incrementally removed observations at random, increasing the number of missing data points. So here we removed 1 observation. Here we remove 2 observations. This is the third case. Here we remove 3 observations, and we have the 5th case and the 6th case. So this is the table for variance estimates for case 2, for case 3, for case 4, for case 5, and for case 6. Good, sorry. So we have that in figure 1, we have an illustration of the performance of the different estimation methods across all cases, and our method is here in yellow line and shows the lower values. So, in conclusion, we introduced the BSA-EM method for variance component estimation in linear mixed models, particularly under scenarios with missing data. Traditional methods often face challenges related to bias in the presence of unbalanced data sets. The proposed BSA-EM method addresses these limitations by integrating the expectation-maximization algorithm for missing data imputation with Bayesian-Stochastic Approximation for variance component estimation. We conducted a numerical study where the BSA-EM consistently outperforms the traditional methods. And I will finish and thank you for your attention.